All right, so in the last lecture, we used the Fourier series analysis to analyze the other two types of equations, the parabolic and elliptic equations. We saw that for parabolic equations, we could explain the behavior of smoothing out of the solution, right? So we do remember if we have the parabolic equation with u equal to 0 but kappa not equal to 0, and we have a very oscillatory solution on one side and a smooth solution on the other side, we see the oscillation is going to be decreased very fast, and the slower oscillating component or part of the solution is decreased at a much slower rate. And we could explain that by looking at Fourier series. And we find that the higher frequency components gets decreased according to an ordinary differential equation, right? dA, d amplitude dt is equal to minus some constant times the amplitude. And that constant, the exponential rate of decay, which comes from the solution of that ODE, is higher for higher frequency components. Right, so if k is the frequency, the rate of decay is actually proportional to k squared for parabolic equations. Now let's look at what actually happens for hyperbolic equations. Do I have another page? No, okay. So for hyperbolic equations, let me get me another page to do the Fourier analysis. All right. So if we have hyperbolic equations, we can do the same Fourier analysis we did in the last lecture. And the same Fourier analysis is going to be also used to analyze our discrete numerical scheme for solving these equations. So it's actually going to be very useful here. So we are going to write our W as a function of x and t, being a summation of k goes from 0 to infinity. Let's still use our ak times cosine 2 pi kx plus bk times sine of 2 pi kx. So that's our Fourier series, right? Here, my ak and bk both depends on t, as w depends on t, while these sines and cosines, of course, does not depend on t. Now when you take the derivative to time, what happens is that the cosine and sines does not depend on t, right? So the derivative to them is 0. Ordinarily, if you write a function as the product of two functions, when you take the derivative, you get the summation of two terms. Each term, you take derivative to one of the components. And here, because the derivative of the sine and cosines to t is equal to 0, so that term automatically goes away, and we only have the term dA dt, right, times the other term. The potential other term in the derivative is ak times the derivative of the cosine to t, which is equal to 0. Okay, so then we take the derivative of the second term, and we get that. Now, what is the other component? U times partial w partial x. Again, we have to take the derivative of the product. But in this case, the derivative of a with respect to x is equal to 0 because a is only a function of t, right? So we have ak here, and we take derivative of cosine, which is what? Yes, we get minus 2 pi k times sine of 2 pi kx. And the second term is bk times 2 pi k times cosine of 2 pi kx, right? So now we get a little bit different behavior from what I got last time. Last time when we were taking the second derivative, the cosine is still going to be a cosine, and the sine is still a sine. In this case, they get switched. So we get a slightly more complex ordinary differential equation. It's actually not just a single ordinary differential equation, but two coupled ordinary differential equations. Because now I have to match this term against this term. Let me use color. I have to match this term against this term, and I have to also match this term, the green term, against this green term, because they are both cosine over here and they're both sine over here. So the matching is going to give me, let's do the green first. The green is dak dt is equal to 2 pi k times bk, right? And then we do the blue term. The blue term is going to give me dbk dt is equal to, don't forget the minus, 2 pi k times ak. Now this is probably also a very elementary ordinary differential equation for you guys to solve, right? So anybody recognize this equation, and how do you solve it? What's the solution to this equation? So are you suggesting we are substituting one equation into the other? Right, so we can do that, and let's do that. You have another? The solution, yeah, is a sine and cosine, but how do you do that? You actually, one way to do it is to actually substitute, for example, this a into here, right? So if I convert the second equation to ak equal to minus 1 over 2 pi k times dbk dt, and we substitute into here, we get that minus 2 pi k times the second order derivative to b is equal to 2 pi k times bk, or equivalently the second order derivative of bk is equal to minus 2 pi k squared times bk. So maybe some people recognize this equation a little bit more readily than the coupled system of equations, right? So what is this equation like? In math or in physics, right? I'm sure you run into this equation at one place or another. What does this equation describe? Waves? What kind of waves? Right? Huh? A harmonic oscillator, yes. I mean, wave is usually a phenomenon of space and time, right? So waves are usually described by PDEs. Well, this equation is an ODE, only a function of time. So a harmonic oscillator, right? Spring mass system, right? Or a capacitor, inductor system, whatever you call it. This one has the solution is basically a harmonic oscillation, a sine or cosine, right? With a frequency again of 2 pi k. Another way to think about it is you can write another way. I also want to teach you to think about that way. Is you need to think about the derivative of ak and bk as a single system of ordinary differential equations with a matrix times this vector of ak, bk. And what is that matrix like? Huh? Yes, you get 0 and 0 over here because the derivative of ak does not depend on ak, right? So something you have to be very good at in this class is linear algebra. I mean, you have to be able to visualize how matrices multiply with vectors and matrices. So derivative of ak is equal to this entry times that entry plus this entry times that entry. So that's how matrix and vector multiplies. Right, so these two are going to go together, these two are going to go together, and it forms this. And similarly, the second row. So this thing that is multiplied with bk has to be this 2 pi k. So I'm going to just write using green here. 2 pi k actually appears here, and this minus 2 pi k is going to appear here.